Hi, this particular talk will deal with the measurement instrument, sometimes known as the measurement information model. It's pretty much the same thing. The information model establishes a defined structure for relating different measurement concepts and terms. It establishes a foundation for consistent measurement terminology and definitions. It's a definition of, as I say, the measurement instruments. You've got your measurement scales, and this is how do those scales combine in order to give you the measures you're after. It's probably not very clear on the slide, so I might have to do something about giving you a separate diagram of it. This is taken directly out of ISO 15939, the software measurement process standard. And I've yet to see a better one. So when you're constructing a measurement instrument, you start, if you want, at the bottom with the entity of interest, which has attributes. And you measure those attributes by mapping characteristics of the entity of interest, which are represented by variables. You map those characteristics to some measurement scale to give you base measures, which is the next level up. Right? Then you may combine those base measures in some sort of a measurable concept to give you a derived measure, one or more derived measures. You combine one or more base measures to give you a derived measure, and you combine one or more base and derived measures to give you other derived measures. And ultimately, it's the combination of these things that eventually finishes up with an analysis model. So you've got a model for your analysis that gives you some indicator, which is then interpreted to give you an information product. Does that make sense? So you get through, and as I say, you get your number 42. Is that good or bad? Well, that's the result from all the analysis. So that's your indicator. Oh, sorry, that's your derived measure, and it will be your indicator. Now, the interpretation of is that good or bad becomes your interpretation and gives you your information product. Now, 42 would be good if more is better and 20 was average. So 42 would actually be pretty good. That's twice the average. But it wouldn't be so good. Let's see, you're talking about environmental things. How polluted is it today? Well, the measure of pollution is likely to be particles in the air of different varieties. What else would be there? CO2, the amount of CO2, the amount of pollutants in the air, and possibly a smog index or something like that. And we'd combine all these things to give you some sort of a result. Is that good or bad? Well, compared to what? Compared to normal for the day, compared to normal for the year, compared to last year, that is where your interpretation comes in. The example I'll go through is an example of productivity, because obviously in software development, people are always interested in productivity, since they want to treat everybody like some sort of a factory. But a decision maker in this example needs to select a specific productivity level as a basis for project planning. All right? Now, this is a fairly reasonable thing to do. You can't just throw it out there and say, well, we'll be done when we're done. We have to have some idea of how many people will it take doing which task at which rate of work, and how much work is there in order to get the project finished, and when is it going to finish. So trying to determine productivity is a reasonable thing to do. Now, the measurable concept is that productivity is related to effort expended and the amount of software produced. Okay? So how much work and how much effort is going to take to do all that work. Thus, effort and code are the measurable entities of concern. This example assumes that the productivity is estimated based on past performance, thus data for base measures, the number of entries in the table below, needs to be collected and derived derived measure computed for each project in the data store. So we want to know what was the productivity of previous projects in order to predict what productivity of this project is going to be. Now, regardless of how the productivity number is arrived at, there is uncertainty inherent in the software engineering. It means there's considerable probability that the estimated productivity will not be realized exactly. Estimating productivity based on historical data enables you to produce something, but it's going to be an estimate. And this is, I guess, is a problem with so many things. Knowledge of the past is only a predictor of the future, is not an exact science. So this applies to all sorts of things. So with something like productivity, in planning, you're trying to predict the future. So historical data will indicate what it's likely to be, but can't guarantee it. Formally, again in ISO 15939, we map things out in a table which gave some formality to how we specified a measure, and that's an example of it there. So going through it, we have the measurable concept, which is the project productivity. The relevant entity is the software produced in past projects and the effort expended in past projects. The attributes will use user stories to measure the size of the software, and we'll use timecard entries to measure the effort expended. Base measures project X user stories and project X hours of effort. So we have base, having determined what we're going to measure, then we have the base measures, and we define exactly what it is in what units that we're going to measure it in. The measurement method, in this case, fairly simple. We simply count the user stories in project X, and we count the hours in project X as well. The type of measurement method is very objective, so we're not dealing with some sort of process assessment, which is a mapping of expert opinion onto some sort of a scale in a certain amount of objective fashion. So we're not dealing with that. We're also not dealing with function point counting. We are dealing with specific objective numbers. The number of user stories is very objective. It doesn't require any interpretation, so it's a very objective thing. The measurement scale for user stories is integers from 0 to infinity. And we can't have a half a user story, so it's going to be integers. Whereas the number of hours could have fractions, so it's going to be real numbers. The unit of measure, count of user stories. Unit of measure in the other one is an hour. The derived measure is project X productivity, and the indicator is the average time to implement a user story. So our indicator, we're dealing with the average time per user story. I know that in this particular case we're not dealing with a standard deviation as well, so which could be interesting. The model for the method of doing things, we compute the mean and standard deviation of project productivity values, and the decision criteria is we compute confidence limits based on the standard deviation, which will indicate the likelihood of an actual result will be close to average. So there is an example there when something quite as simple as productivity, because there are so many different ways that people measure productivity, talking about the productivity of a project in general is I suppose not that good, because you get different people. People mean different things. Well, people are interpreting it differently. So when it gets down to it, you have to specify exactly how you're going to measure this thing. So that's an example of a measurement instrument, all set out in quite a formal fashion. In your research, your measurement instrument may be quite simple or may be quite complicated. Now, if you are doing surveys and you are measuring different attributes, I strongly encourage you to sit down and plan your measurement instrument so that you can deal with some of the problems you're likely to encounter. Alright, So that was the measurement instrument.